Welcome to AI Paper Podcasts. Today we're embarking on a deep dive into a paper that honestly sits right at the cutting edge where quantum computing meets machine learning.
Yeah, this is fascinating stuff.
The research we're digging into is titled Embedding-Aware Quantum Classical SVMs for Scalable Quantum Machine Learning. It's by Sebastian Andres Cajas Ordóñez and his team.
A really insightful group.
And our mission, as always, is to cut through the, let's say, the dense academic language and pull out the key insights for you, especially if you're a technical pro trying to stay ahead.
Right, distilling it down.
Exactly. So let's start with a quick 1-minute summary, kind of the essence for our short-form clips later, the core problem. Quantum machine learning, particularly quantum support vector machines or QSVMs, holds huge promise.
Immense promise.
But they hit this massive wall. Scalability. You've got these high-dimensional quantum states, hardware limits. It's tough.
And what's truly fascinating here, what this paper brings, is their hybrid solution. It's quite clever, actually. They call it an embedding-aware quantum classical pipeline. Essentially, it combines smart data reduction using class-balanced k-means with really powerful pre-trained vision transformer embeddings. You know, VIT embeddings.
Ah, VIT. Okay. And here's where it gets really interesting, the big reveal. They found that these VIT embeddings are uniquely suited to unlock what they're calling quantum advantage.
That's the key term.
We're talking significant accuracy bumps up to 8.02% better than classical SVMs on fashion MNIST, which is not trivial, and 4.42% on MNIST.
Which is pretty impressive for MNIST too, given how well classical methods already do.
Right, but the kicker, the surprise.
Yep.
Traditional CNN features, the kind you might expect to work well.
Yeah, from models like EfficientNet.
They actually made things worse when fed into the quantum system. Performance went down.
Which really makes you pause and think, doesn't it? It raises this important question. Why this specific combination? Why VOW? And their work gives us the first sort of systematic proof that this quantum kernel advantage isn't automatic. It critically hinges on the embedding you choose beforehand.
So it's not just plug and play with quantum.
Not at all. It suggests this fundamental synergy, maybe between how transformer attention works and how quantum feature spaces operate. It's basically a practical roadmap for scaling up QML using architectures we already know, like transformers. That's a big step.
It really is. And that sets the stage perfectly for why this research matters so much right now. You know, we hear about quantum computing being transformative.
The next big paradigm shift, potentially.
Yeah, for tackling problems classical computers struggle with. And meanwhile, machine learning is just accelerating like crazy.
Driven by data and hardware, yeah.
So QML, quantum machine learning, sits right at that intersection. It holds this promise of handling, super high dimensions, complex relationships, using quantum tricks like superposition and entanglement.
Absolutely. But let's be realistic too. There are big practical hurdles still. Large-scale quantum computers. They're noisy. Decoherence is a huge problem. The quantum state just falls apart.
Right, the environment interferes.
Exactly. And while there are error correction methods, they're incredibly complex and need way more qubits than we currently have reliably.
So we see these cool proof of concepts like on Google's Sycamore or IBM's machines.
Yeah, impressive demos. But there's still a gulf between that and something you can reliably deploy in industry.
Okay, so how do we bridge that gap?
Well, one really promising strategy, and this paper leans into it heavily, is using classical pre-processing. Think dimensionality reduction, like PCA.
Principal component analysis, yeah.
Or even using neural networks like variational autoencoders to compress the data first, learn a more compact representation.
Kind of prepping the data before it hits the quantum computer.
Precisely. These hybrid approaches are key right now. They have managed the limited qubits we have, make the quantum part feasible, while still trying to harness that quantum power for the classification itself.
Okay, so facing those challenges head on, Ordóñez and the team came up with this specific hybrid framework. Let's unpack that.
Right. Their framework is designed specifically to tackle those scalability issues.
Right.
The core idea is to shrink the data dimensionality while keeping the important bits, the task-relevant structure.
Smart reduction.
Exactly.
Right.
And then the actual quantum classification, they do that using Tensor Networks simulation. It's a clever way to simulate quantum systems more efficiently on classical hardware, especially using accelerators like NVIDIA's QTensorNet.
Okay, so simulating the quantum part, but doing it efficiently.
Yes. And the results. When they tested it on MNIST and Fashion MNIST standard benchmarks, it consistently beat both classical SVMs and other simpler quantum approaches. Better accuracy, better efficiency.
Let's break down that pipeline. You mentioned stages. What does it actually look like?
Yeah, they lay out an 8-stage process, but you can think of it in chunks. First is data prep. They start with image extraction, obviously. Then comes this really crucial data distillation step. They use class-balanced k-means clustering. Think of it like finding representative prototypes for each class.
Instead of using all 70,000 images.
Exactly. They cut it down to just 2,000 samples, 200 per class. That massively reduces the computation needed for the kernel matrix, like from O70,000 squared down to O1600 squared for training. Huge difference.
Now, okay, that makes the quantum part actually possible.
Totally. Then, embeddings extraction, they use pre-trained models, efficient at B3, and crucially these vision transformer variants, trained using CLAP. These capture really rich features.
Got it. So distillation, then embedding. What's next in prep?
Final prep step is data compression. They use PCA to squish those embeddings down even further to dimensions that fit onto their simulated quantum hardware, like 16 qubits, which corresponds to 16 dimensions here.
Okay, so distill, embed, compress. Now the data is ready for the quantum stage.
Yeah. Phase 2 is quantum model application. This starts with quantum model design. They set up a QSVM using something called the Tensor Networks Support Matrix Framework. It's basically a technique to represent the quantum circuits efficiently as networks.
Makes the simulation tractable.
Right. Then model training, feeding those compressed embeddings into the QSVM. After that, standard evaluation using cross-validation to check performance. And finally, a test on the validation set the holdout data to see how well it generalizes.
And the quantum model itself, the circuit they used, is it standard?
It builds on existing work, specifically a framework by Chen and others. You can picture it. Qubits get initialized, then data gets encoded using rotation gates. The parameters depend on the input features. Then, crucially, CNOT gates create entanglement between the qubits.
Which is where the quantum magic is supposed to happen, right? Capturing complex correlations.
That's the idea. Then another layer of rotation gates. This whole sequence forms their embedding-aware quantum feature map. And the kernel, the similarity measure, uses a compute-uncompute strategy, a neat quantum trick. The whole thing gets mapped to tensor networks for simulation.
And you mentioned they didn't just use existing simulation methods, they improved them.
They did. They added some practical performance boosts. Smart stuff, really.
Like what?
Things like function-level caching at cache in Python, so they weren't recomputing the same gate matrices over and over.
Makes sense.
Pre-computing trig values, sine and cosine, that pop up everywhere in quantum circuits. And optimizing how they generated batches of operands using list comprehensions instead of slower iterative methods.
So these little engineering tweaks add up.
Absolutely. They called their improved version Baseline Plus, and it significantly cut down runtime and memory compared to the original baseline implementation they started from. Saved like 680 seconds just in cross-validation. That's substantial when these simulations take time.
Yeah, over 10 minutes saved per run adds up fast. Okay, so they've got this optimized pipeline. Let's talk about that quantum kernel again. What's the core idea there?
Fundamentally, the quantum kernel measures the similarity between two data points in this high-dimensional quantum feature space. It's calculated as the transition amplitude, basically, the overlap between the quantum states created by their parameterized circuit for each data point.
And the theory is that this quantum space is much richer than classical feature spaces.
Exactly. It grows exponentially with the number of qubits, 2 to the power of n. That's where the potential for quantum advantage lies. But, and this is the paper's crucial insight, realizing that advantage isn't guaranteed. It's critically dependent on how you map or embed your classical data into that quantum state first.
It's not just the space, it's how you use the space.
Perfectly put. It's about the input representation.
Okay. And to test this, they used standard benchmarks.
Yep, good old embolized handwritten digits.
Everyone knows MNIST.
In Fashion MNIST, which is a bit tougher with images of clothing items. Both grayscale, 28 by 28.
Yeah.
And remember that data distillation, reducing to 2,000 samples made, running these complex QSVMs feasible.
Right. And the embeddings they compared.
They used efficient at B3, pre-trained, giving 1,536 dimensions, and then several VIT variants, also pre-trained via CLAP, giving either 768 or 512 dimensions.
And PCA squeezed these down to 16 dimensions for the 16-qubit simulation.
That's right. And importantly, for comparison, they ran classical SVMs with a standard RBF kernel using scikit-learn, but critically using the exact same PCA compressed feature representations. So it was a fair fight, apples to apples on the input data.
Good experimental design. And they ran this on serious hardware.
Oh, yeah. NVIDIA A100 GPUs, 80 gigs of memory, using CLEA and NVIDIA's QTensorNet library for the Tensor Networks simulations. You need that kind of power.
Okay, drum roll time. Let's get to the results. What did they actually find? This is the core finding, right?
This is the absolute core. It's pretty stark, actually. They found consistent performance improvements for the QSVMs over classical SVMs, only when using the vision transformer embeddings.
Only with a VAT.
Only with VIT. When they used raw pixels, or the features from EfficientNet, the QSVM performance dropped. It was worse than the classical SVM.
Wow. So the quantum system actually performed worse with those features.
Yes, which is striking. Let's look at the numbers. They really tell the story.
Lay 'em on us.
Okay, on MNIST. Classical SVMs were already doing great, like 94, 98% accurate, depending on the embedding. QSVM with raw pixels, performance dropped by over 6%, with EfficientNet embeddings dropped by 2.5% to 3.5%.
Ouch.
But with VT embeddings, the QSVMs improved accuracy by up to plus 4.42%. One VT configuration hit 99.5% accuracy.
That's near perfect on MNIST.
Pretty much. Now, Fashion MNIST, the harder one. Classical SVMs were around 78-91%. Again, raw pixels and EfficientNet features led to QSVM degradation down 3% to almost 7%.
So same pattern.
Exactly. But with VIT, boom, QSVMs showed gains of up to plus 8.02% accuracy. Both top VI2 configurations reached 90% accuracy.
An 8% jump on Fashion MNIST is significant.
It's huge, and every VIT variant they tested showed positive quantum advantage. This isn't some random fluctuation. It points to that deep compatibility we talked about.
So the takeaway isn't just QSVMs are better, it's QSVMs can be better if you feed them the right kind of features, specifically transformer-style features.
Precisely. The future representation is just as important, maybe even more important in this context, than the quantum algorithm itself.
So for someone listening, maybe an ML engineer thinking about future systems, does this mean we should be favoring transformer-based embeddings even now, just in case?
That's a really interesting strategic question. This paper strongly suggests that yes, the way transformers learn representations, maybe through that attention mechanism focusing on global context, seems to produce features that mesh really well with these quantum kernel methods. So designing embeddings with potential future quantum compatibility, it might actually be a smart long-term play.
And that 8% accuracy gain, sometimes in research papers, small percentage gains don't feel huge, but in the real world.
Oh, absolutely.
Yeah.
In applications where high precision is critical, medical diagnosis, finance, safety systems, an 8% gain can be the difference between deploying a model and not. It's substantial value.
Were the results stable?
Reproducible.
Very. The cross-validation showed really low standard deviations, like 0.003 defined A or 0, MHIO 00200. That means the results are consistent, not just lucky runs.
Good.
And the VIT-based quantum models, they consistently got near-perfect AUC scores, area under the curve, often around 99.9%. That suggests they're really good at distinguishing between the classes. The confusion matrices also look great, strong diagonals, few off-diagonal errors, good generalization.
Okay, but what about the elephant in the room? Compute time. Quantum simulations are notoriously slow. True, it's definitely a factor. Most of the VIT configurations took around 3D seconds. That's over an hour for training and evaluation on their hardware. And memory usage was around 43 GB.
So not instant.
Not instant, no.
Right.
But you have to compare it to the potential alternatives. Getting similar accuracy gains classically might require vastly larger data sets or much more complex classical models, which also have high computational costs.
Right, it's a trade-off.
Exactly. And considering these are complex, high-dimensional embeddings being processed by a simulated quantum system, 3D 800 seconds is actually quite efficient compared to where things were a few years ago. They even found one VIT configuration, VIT B7552, that hit a sweet spot. 97.3% on MRS with the fastest runtime of 3,763 seconds. So you can optimize for that balance.
So let's synthesize this. What's the big message for, the technical pro listening to this? It feels like it fundamentally shifts how we should think about quantum advantage.
I think it absolutely does. The script is flipped, like you said. Quantum advantage isn't just going to magically appear when we run a quantum algorithm. It emerges from this strategic synergy. That's the key word, between the quantum kernel and the right kind of input data representation.
It's like you need high-octane fuel for the quantum engine. You can't just put regular in and expect rocket performance.
That's a perfect analogy. The VIT embeddings are like the high-octane fuel here, the CNN embeddings. Maybe like regular unleaded works okay in a classical engine, but doesn't ignite properly in the quantum one.
So the practical implication is co-design, thinking about algorithms and data prep together.
Yes, algorithm representation co-design. That's the future, according to this work. And while the compute cost is significant now for those high-precision applications, it might already be justifiable. Plus, their data distillation method shows a path to making these quantum kernel methods tractable, usable, even with current simulation capabilities.
So it's a practical pathway, not just theoretical potential.
Exactly. A pathway that should only get more appealing as actual quantum hardware improves and simulation gets faster or less necessary.
Okay, but no paper is perfect. What limitations did they acknowledge? Where do we need more research?
Right, they were clear about that. The evaluation was on MNIST and Fashion MNIST. Relatively simple, grayscale, well-behaved data sets.
Need to try it on harder stuff.
Definitely. CFAR10, ImageNet, maybe real-world medical images. We need to see if this VIT synergy holds up on more complex, diverse data. Also, the deep theoretical reason for this transformer quantum link is still mostly unexplored. That's a huge area for future fundamental research.
So lots more work to do there, and future directions based on this.
While automating the choice of embedding in kernel, maybe using meta-learning or reinforcement learning, finding better dimensionality reduction than PCA, maybe something nonlinear that preserves more structure, and of course designing even better, more efficient quantum circuits.
Expanding to new domains too, you mentioned medical imaging.
Critical. Demonstrating value on real-world high-impact problems is the next major hurdle.
So summing it all up, the big takeaway.
The big takeaway is achieving quantum advantage in machine learning isn't just about having a quantum computer. It's about smart design, specifically this co-design of the classical data representation and the quantum algorithm. How you prepare the data for the quantum system is absolutely fundamental.
It's a shift from focusing only on the quantum black box to understanding the entire pipeline, especially the input.
Precisely.
And the really interesting part for people listening, this research offers immediate food for thought for current ML practices, especially around embeddings, but also provides a concrete, scalable foundation for future quantum ML that cleverly leverages the power of modern architectures like transformers. It feels like a genuinely viable path forward.
I agree. It connects the dots between cutting-edge classical ML and the potential of quantum.
For those of you who really want to get into the weeds, the code for the study is actually up on GitHub. We'll make sure to link to the paper and the repository in our show notes so you can explore it yourself.
Definitely worth checking out if you're interested.
Well, thank you for joining us on this fascinating deep dive into the latest intersection of AI and quantum computing. Keep learning, keep exploring those complex feature spaces, and we'll see you next time on AI Paper Podcasts.